In this we'll be looking at stationary waves, also known as standing waves, how they're formed, what they are, and we're also going to have a look at these terms here, so nodes and antinodes, and these are just some characteristic features of the stationary waves that we're going to be having a look at, but we're going to be able to define them. So we'll start off with this diagram. So this sort of covers it all, but we'll go through it piece by piece. So before we look at standing waves or stationary waves, let's make sure we're happy with the concept of a progressive wave. So a progressive wave is one which travels forwards in space, so like a sound wave, it starts at a speaker, progresses forward through space, carries energy, carries information to your ear or a microphone or whatever. A standing wave is one where, rather than carrying energy, there is no net carrying of energy, and it's formed generally by two progressive waves. So here in this diagram we've got one progressive wave marked in red, one progressive wave marked in blue. And so we can imagine this is two waves travelling in opposite directions on a length of string, for example, or two sound waves travelling in opposite directions. These stationary waves can form from either longitudinal or transverse waves. So we've got the red travelling to the right, so you can see up in this first frame the red starts here, down here it's moved to the right a bit, here we've gone a little bit further, we carry on, and so on. So that's what we've got going on in this diagram, and the blue is travelling in the opposite direction, so it starts at this point, by here it's travelled across to there, here we're up there, here we're there, here we're there, and so on. So we've got these two progressive waves travelling in opposite directions, and for these to be able to form a standing wave, what we need is these are travelling with exactly the same frequency and also with exactly the same amplitude. If those two criteria are not met, then we won't get a standing or a stationary wave. So with a stationary wave there's no net propagation of energy, so if these two waves travelling in opposite directions have got different amplitudes, that will correspond to a different amount of energy going in each direction, or similarly different frequencies would correspond to different amounts of energy. So let's see what happens when these two waves start to overlap. So here we've got them already overlapping, and whenever we have these two waves overlapping we're going to get interference, we're going to get superposition. So at each point along this piece of imaginary string, all of the amplitudes, all of the displacements are going to add up. So we can see here, for example, we've got the two peaks lined up, and so we get a lovely big peak in this black net wave. So the black is what we actually see due to these two overlapping. Over here we have the two troughs lined up, and so we get a very negative region there, so a huge trough. Here we've progressed a little bit further, and so the black wave is slightly decreased in amplitude. So here, for example, the blue wave has zero amplitude, but we've still got the positive from the black wave, so on and so forth. Here we've progressed a little bit further, so you can see from here the red has continued to the right a bit, the blue has continued to the right a little bit. Here we've gone even further, and so now we've gone from being in phase in the first line, we're pi by 2 out of phase, so we've gone a quarter wavelength apart. We've now got a half wavelength apart here, so this has put us pi out of phase, which means we've got destructive interference. And then we continue on, they start to fall back in phase, and so we get constructive interference again. Now along this region I've marked in a couple of lines which we can use. So these are used to identify the node. So let's follow this leftmost dashed line, so the close packed dashes, and you'll see that in the top portion we've got no displacement. We come down a bit, we've got no displacement. In the next one we've got no displacement, and in the next one, slightly misaligned there, no displacement, no displacement, and we can see the same if we look at the other dashed line. So even though these two waves are travelling in opposite directions, even though at this point, for example, there is a displacement on the red wave and a displacement on the blue wave, they cancel out, and so everywhere along these lines we get no displacement. If we look at these wider dashes, then we can see if we follow the left one, we've got a large negative displacement. It reduces, passes through zero, and then we get a maximum positive displacement. Following this one here, we've got a maximum negative displacement, and coming back up to the top, here we've got a maximum positive displacement. And so this is the pattern we get. So we've got the nodes and the antinodes are what these dashes represent. So these nodes are the regions in the standing wave where we have zero displacement. Or for the firm definition, it's any point on a stationary wave where there is no displacement of the particles at any time. So we can see there's no point in time here where there's any displacement at all about these nodes. At these peaks, this is called an antinode, so this is the opposite. So here we have the maximum displacement at any given time. So at this point, this is the maximum displacement of this wave. Here there's maximum displacement of this wave, which is 0, and so on and so forth. And we can see what this looks like when it's animated. So here we've again got the blue and the red waves travelling in opposite directions. And you can see that we've got the black wave, and it's oscillating in this manner. So the black wave isn't moving left or right, it's just moving up and down. And so this black wave is what we see. This black wave is the stationary wave. So when we've got these two progressive waves travelling in opposite directions, and that might be because we've got two sources, or it might be we might have, say, one source over here, we're projecting our wave along towards the right, and somewhere off the right hand side of the screen there's something causing the wave to be reflected back, and that reflection is causing this overlapping. So whenever we've got these two progressive waves with the same wavelength, same frequency, same amplitude, travelling in opposite directions, we're going to get this standing wave that looks like this. So here, these red dots, these are our nodes, and you can see at any point in time there's zero displacement at all times. And then halfway in between those we've got the points of maximum displacement, the points where we reach a large amplitude, and these are the antinodes. So we've got the nodes, antinode, node, antinode, node, antinode, and so we get this alternating pattern going between them. Now it's worth noting, if we pause this at some point in time, so if I pause it there, say, then you can see that the red wave has a full wavelength coming from the start over here on the left to here, and the blue wave, because we're at maximum, we're in phase, also does the same. And so the distance between adjacent nodes, or the distance between adjacent antinodes, is actually only a half of a wavelength. And so if we saw some standing wave pattern and we wanted to know the wavelength or frequency of the wave that was forming it, then we'd have to determine the wavelength by the measurement between two nodes rather than the measurement between one set of nodes. So we'd measure from this node to the next node, and then the second node would give us the full wavelength. Of course, we don't actually see the red and the blue wave travelling, we just see the net displacement of those waves at any given time. Just like when we're looking at a diffraction pattern, we don't see the two waves from a pair of slits, for example, we just see the net result when they superimpose, when they interfere with each other. And so on this piece of string, this is all that we would actually see. This is all that we see as the net result of these two propagating waves travelling in opposite directions with equal frequency, equal amplitude, forming this repeated pattern of nodes at the red points and antinodes in the middle between them.